Ki te tangi e te manu e karanga nei tui tuia. Tuia ki runga, tuia ki raro, tuia ki roto, tuia ki waho, tuia te hera tangata. E na mana, e na reo, e ra rakatira mā, tēnā koutou, tēnā koutou, tēnā koutou katoa. Tēnei te raro e te maru o ka mana whenua, ka te māmoe waitaha kaita who know my haramai. Welcome. I stand here on behalf of, under the umbrella of the people of this place, ka te māmoe waitaha kaitahu, and welcome you all to this beautiful occasion for an inaugural professorial lecture. Ki te whare, tūnei, tēnā koe, tū tonu. To the house that stands here, greetings, may you stand forever. But if there's some doubt about that and there might be some shaking or an emergency, please follow instructions of people involved. Note where your exits are, and in an earthquake, drop, cover and hold. And mate haere hoki atu rā ki te pō. To those that have passed, we remember you, may you pass into darkness. Particularly, we remember you at this time of Matariki. Ko wai ao, no Otapoti ahau, ko Katarani te iwi, hei kaimahi ahau te o tāko whakaihu waka, ko Richard Blakey, tāko ingoa. So greetings everyone, who am I? My name is Richard Blakey. I'm Deputy Vice-Chancellor for Research and Enterprise here at the University of Otago, and I'm your MC tonight. I bring apologies from our Acting Vice-Chancellor, Helen Nicholson, who would love to have been here. I'm Kotarani te iwi, Scottish by background, and I work here at the university. I did use, I think probably a little bit without permission, our new name, Māori name, o tāko whakaihu waka, which I think, David, you should take pride. You are the first IPL after this name has been officially endorsed by our University Council this afternoon. It's a very historic day for the university to have approved for rollout from May 2024, but the University Council agreed today to approve a brand and identity project that incorporates the accepting of the gift from mana whenua of the new name Otaku Whakaihu Waka, which translates, Otaku is the regional name but talks about the harbour and the currents that flow in and out. Whakaihu Waka talks about the bow of the waka that pierces the waves first, and this being a place of many firsts, including us being the first university, is a name that we accept with pride. For research, it is also important to know that research is at the front of the waka that pushes forward the waves and allows others to follow. So welcome to you all. Ki te rangatira tēnā koutou, to the important people in our academic party, Professor Barker, PVC Sciences, welcome. Dr. Mills, Head of Department, welcome, and particularly to you, David, welcome for this auspicious occasion. We're really pleased to also welcome members of the university community, members of the public of City of Dunedin, members of from wider and further afield, particularly those who are joining us online in real time or through the recording of this that will go up on YouTube at some point. And in particular, warm greetings to your special visitors here today, your parents, Michael and Kerry, tēnā kōrua, your wife Giselle and your son Robbie who are here. I hope you have a great time, and to those in your family and friend groups who are joining us online. Before David talks, Professor Barker will give a more detailed introduction, but I'll just emphasize to you all here today the importance that we place on inaugural professorial lectures. We get dressed up for the occasion. It's an academic occasion to be celebrated because promotion or appointment to professor at the University of Otago is a big deal. We do ask a lot of our professors, and we do measure when people apply for promotion to that rank, those applications against some stringent criteria of requiring significant leadership and competence against teaching, research and service. And in particular, I want to acknowledge your leadership, David, and the things that I've very much appreciated is what I would call leadership through partnership, that you demonstrate in your research. I note your research supervisions are very very normally no more than 60% to any one individual. You work with teams very well. And in terms of your service in particular, you have contributed very strongly to the e-research advisory group, to national leadership through the national e-science infrastructure, and sitting on our IT governance board. You provide great leadership, and it's a very collaborative set of leadership that you provide. Before I hand over to Richard Barker, though, I do want to identify that it's great for me to be here because we also share a lot in common. Gender, we share one alma mater. I think we started here at the University of Otago in the same year, but also we're members of an esteemed professional body, the Institution of Electrical and Electronic Engineers, the IEEE. And that means, look, electrical and electronic engineers are a very special breed because you cannot spell geek without EE. And so I'm really looking forward to hearing what you have to say. So on behalf of the university, David, congratulations. Please join me in congratulating David on this well-deserved promotion as I invite Professor Barker up to give you a more detailed introduction. So well done.
Professor Blakey, tēnā koe. Professor Ayers, tēnā koe. Professor Mills, tēnā koe. Friends and colleagues, tēnā koutou, tēnā koutou, tēnā koutou katoa. It is my great pleasure to introduce our speaker tonight, Professor David Ayers, who comes from the soon-to-be extinct Department of Computer Science to give his inaugural professorial lecture at the University of Otago. For those who are not in the know about that mysterious reference, our University Council, and kia ora to one of our councillors present with us today, endorsed our proposal to merge the Departments of Computer Science and Information Science at the University of Otago. Hence the impending extinction of computer science as a department. As indicated by Professor Blakey, David was promoted to professor in February of this year, and tonight we celebrate this significant achievement. David was born in London, and according to the information that he gave me, he says he then moved back to Australia, which hints at some kind of pre-life. He was brought up in Sydney, and I just discovered in the beautiful environs of Bondi Junction, an area that I spent a little bit of time growing up in as well, a delightful area. And it was in Sydney that he went to school, or school as they say over there, and then on to the University of New South Wales, where he graduated with a combined first-class honours in engineering and science, majoring in computer engineering. This honours degree led him back to the land of his birth, where he completed a PhD at the University of Cambridge, graduating in 2006. A member of King's College, he was their IT consultant and webmaster during this time. His PhD was then followed by a sequence of research fellow appointments in the University of Cambridge Computer Laboratory that filled the intervening years before he was appointed to take up the position of lecturer in our Department of Computer Science. This lectureship was taken up in 2011, so David's rise through the ranks from lecturer to full professor have taken just 11 years, which has been rapid and really is a measure of his all-round excellence. As we have heard from Professor Blakey, promotion to full professor at the University of Otago is far from easy. You must excel in all of the academic domains of teaching, research and service. There cannot be any weaknesses, and Professor Ayers has truly excelled. David's research is measured by its impact and by the regard of his peers. And here I'm going to draw heavily on referee statements in support of his application to make this point. These highlight that he is a highly respected and significant scholar, particularly known for his work in distributed systems. This work is highly cited, with 8 of his publications receiving more than 100 citations. Many published papers in academia, sadly to say, don't get any, so 100 is truly spectacular. That we also saw or heard that his work on operating system security has been influential in the highly topical field of security breaches, which is of great interest to us today. His safe web system was deployed to protect databases within a cancer registry of the UK National Health Services. We read that he was awarded an A rating in the 2018 performance-based research funding evaluation exercise, which ranks him amongst the best computer scientists in this country. That as a research leader, his wide knowledge of computer science research has allowed him to contribute to research projects across a large number of disciplines in ways that have enabled many projects that otherwise might not have been successful. David is also an excellent teacher, and for this introduction I decided to follow the strategy of reading what others have said about him, and this time I've chosen the words of his students. Quote, "Out of my 2 years at Otago, David is easily the best lecturer I've ever had. He's concise, but explains things with a real enthusiasm for the content he is teaching. David is a fantastic teacher. He is very quick to respond with a great reply on emails. David's the best," that was in caps, so that's for emphasis. "So helpful when you need it, and you can tell he's genuinely interested in the topics." And my favourite, because I learnt a new word, "the only verbal chain gun I've ever known," who can keep me interested for 50 minutes in a row. Extremely knowledgeable, extremely helpful, extremely nice guy. Thanks, David. In addition to providing an enjoyable and entertaining experience for his students, David has also been a curriculum innovator. An illustration of this is his Software Carpentries incubator work on use of Docker for reproducible research, which was the featured incubator lesson in February 2021. Software Carpentries is a worldwide organisation sponsored by 70 universities, and his recognition as one of their worldwide instructors is significant. In service to the professional community, Professor Eyers has been a member of the Board of Directors for the New Zealand eScience Institute, appointed because of his expertise in e-research. He's been actively involved with strategic planning for REANZ, the Research and Education Advanced Network New Zealand, a high-capacity, ultra-high-speed national research and education network connecting New Zealand's tertiary education's research organisations, libraries, schools, museums, to the rest of the world. He's on the advisory boards of the Cybersecurity Research Program and the Science for Technology Innovation National Science Challenge Veracity Lab, and was invited into their Science Leaders Program. He's been active in conference leadership as co-chair of 2017's IEEE Conference on Cloud Engineering and another major ACM DEBS Congress in 2018, and has been on the program committees for more than 120 conferences. In addition to this, David is an excellent university citizen. For the university, he has chaired the e-research advisory group since 2012. He has chaired the IT Portfolio Change Advisory Board since 2022. He's on the project steering committee for cybersecurity and for the Otago Digital Workspace, and has been a member of the Otago Research Information Systems Reference Group. He's active on the steering groups of Catchments Otago and the Otago Energy Research Centre. And the last one I'll mention, which Professor Blakey's already referred to, is David is a member of the IT Governance Board, and that just happens to be a board that I chair. And from the chair's seat, I get to witness it firsthand, the enthusiasm, engagement, and enlightenment that David brings to all of these activities. I think you've heard enough from me. It's now time to hear from Professor Eyers himself, and we're going to hear firsthand about the interests and enthusiasms that have led to this celebration tonight. Please join me in welcoming Professor David Eyers.
Thank you. Thank you. Tēnā koutou, tēnā koutou, tēnā koutou katoa. It's an absolute pleasure to be here. Thank you for the detailed introductions, which give us a good context of where we're going next. I'm just going to click this thing and see where we go. Full screen. That will make me be able to see it slightly better than what we had before. Sorry, we've got a technical glitch here. I'm on the wrong screen. This is not going to be... That's better. Thank you. That was fixed by magic. So I figured that for tonight, with respect to technology risks, the way I was going to avoid any failures was to print out my presentation. So because it's on paper, I don't need to rely on any of this technology working for the whole 45 minutes. However, so far we've blown the central projector, which is why we're using the two side screens, but thankfully we have lots of fine IT equipment in the university, and so we have these backups available to us. But again, thank you for the introduction. To start this kind of event, one might be worried about the quality of one's presentation materials, and certainly I've considered thoughts about whether or not there are errors on these slides. But of course, to begin with, well, we do have one, which has already been alluded to, and that is that the department is wrong because it's going to be made extinct. However, this is a very promising transition. This is a time where we actually get to combine multiple departments who have a focus on computing at the University of Otago and grow into something which is bigger, that will have more reach going forwards in the future. So I might just clean that up slightly, and hopefully it's okay to forge documents from the university. But so this is an absolute pleasure for me. And I will move on to the actual material that's not just about the title page, which is pretty good going because we've already lost a minute or two. I've attended many IPLs in my time at the university. And as those IPLs have rolled past, I have to admit my thoughts had actually turned increasingly to the fact that I might actually be here. And at first, I had this kind of warm feeling that by the time I was going to stand in front of you, I would have a really clear research agenda, and it was completely obvious where my research was going to go next. Time passed, and we got closer to the night here this evening, and I started to have an increased level of panic that actually there was just this gigantic range of different things that I was trying to juggle, and that it wasn't entirely clear where this sort of research agenda was going to wind up. However, in preparing for the IPL, I realized there are actually some running themes in my research. So there you go. Preparation for these IPL events can help you focus on your work, but I must say it's a slightly nerve-wracking way to do so. However, in talking about the trajectory that I'm going to discuss this evening, I am taking one particular pass through the work that I have had. Now, this word cloud in a cloud that I generated on the cloud is actually a set of all of the things I'm not going to talk about this evening. So these topics are things where I have taken extracts from titles of papers or projects or general involvements that I've had with other people. And I'm very well aware that in talking about the particular trajectory this evening, I'm not going to be talking about a whole bunch of other journeys. And so thinking about that, I kind of considered, well, that's partly why tonight I'm not going to be naming a lot of names in the course of the work that I've done, because the sort of focus on naming some is going to end up feeling like I'm neglecting so many others. Everyone I've collaborated with on this extraordinary range of projects I've had the privilege to work with has been extremely important as an influence on me, and I thank you all for all the collaborations I've been able to have. A prelude. And this is a slightly interesting prelude because I'm not 100% sure that all the transitions are going to work smoothly. But like I said, I've got my paper, so it should be okay. How I came to have my head in the clouds in the first place. So I will give a warning right now, particularly given you have this dual sort of screen display, that there is going to be a lot of motion that's about to get kicked off on these screens. So if you don't like motion, avert your eyes now. This completely gratuitous slide transition represents something which I'm going to take you on a journey around that involves heads in clouds. That transition represents a kind of random construction of a move from one picture to another. And there was someone I know who would have found that transition absolutely fantastic, namely me. Because I had, at early days in primary school, this desire to program this sort of random dot transition that takes you from one picture to another. I wanted to, just do one dot after the other, eventually it all accumulates and you get a complete transition. And I knew BASIC, the programming language. And I, at the time, thought that I just needed time. I found some subsequent notes that actually show my working, trying to kind of determine how to do this transition from one kind of pattern to another, programming this in BASIC. Meanwhile, the handball tournaments and learning to spell were passing me by and were things I would have to catch up on later. You also notice that there's a little bit of the engineering tendency that is contained within this sort of picture, and I'm very pleased that I've passed that on to my son, it seems, and I apologize, Giselle, to you. What I will try to do now, though, is take you a little bit, if I can, into my shoes as they were. There we go. So first of all, I need to do a little bit of tweaking. That stuff is too high resolution to be the actual Apple IIe. So These oops, I'm not going to do that multiple times. This machine, one of the things I love about it is it is so immediately accessible. It only has uppercase, so apologies for the shouty look of all of the presentation of material we're going to see here. But what I'm going to do for you is just cheat and load up something which I've prepared earlier. This is an example of a program that I would have known wouldn't have done what I wanted. But I'll guide you through what's happening with this program. Before we do that, I'm going to have to transition and just give you a little bit of a passing shower of graphics and maths that will kind of complete this. If you're going to draw dots on a screen on these computer programs, they're numbered using rows and columns, but of course you can also number the dots continuously across the rows and columns. So in this case, what I'm showing you is the low resolution graphics mode, as it was called on the Apple IIe, which means for its time it has to be super low resolution these days. That has only 40 columns. And so you can see that the beginning of the next row numbers from pixel number 40, if you want to keep counting in reading order. So that's important in terms of how this program currently works. What is it doing? Well, I'm changing to the low resolution graphics mode in line 10, picking a color. I've got this variable called A. That's going to be the dot that I'm going to change. So I'm going to build this program that changes from one thing to another. The number of squares I need to cover is in the variable named ns. Long variable names are good these days, but back here you didn't have a backspace function, so you use short variable names. For reasons that will become clear, I'm storing the next prime number above 800. And then between lines 60 and 130, I'm doing a loop over all of the squares that I might want to pick. We'll have a look here at line 70. What line 70 does is just picks a random number from 0 to the number of squares. So it's just going to pick one dot after another to do our transition. Lines 80 and 90 do corrections that we don't need yet, but I'll lead you through that when we get there. Lines 100 and 110 convert that numbered dot into a row and column location that we can plot. But this program is not going to do what I would actually want. Also, I'm only doing the top half of the screen because these things are so slow, you don't want to have to wait for this to finish, so we don't need to. This is eventually going to not complete this square because of the fact it's got this repeating pattern of random numbers. You'll get repetitions of those numbers, so it's not going to pick all of the numbers. You leave it running forever, that would be tremendously boring, so let's not do that. Let's stop this program, and apologies for the flashing, and let's go and get a little bit more maths. So I'm going to introduce you very briefly to the integer group modulo n. And again, I'm supposed to be an engineer, so I'm probably stepping out of my kind of area of complete daily work, but I think that we can agree we all actually understand how to work in the integer group modulo 7 through the illustration I'm showing here. If you say it's Tuesday, and I believe it is Tuesday, although it's been a bit of a blur recently, you can assign Tuesday to be a 1, and that's shown on the kind of cyclical diagram on the right-hand side of the slide. If I tell you to add 9 days, well, that's going to be a week and 2 days, so we move to Thursday. Now you've wrapped around the numbers, so you've gone beyond the maximum count of 6, but you make a correction to, a correction to that number. I've got a gesture over here. A correction to that number that means that you end up discovering that you've come back to the number 3. So this is something where it turns out what we would actually like is a generator of this group. And so sometime after primary school, because I'm not Euler and I didn't derive this from first principles, sometime after primary school I discovered that this was actually what I was after. A generator that would mean that you would end up filling in all of the different possibilities of this set of numbers. An easy one for the days of the week is what's the next day. You keep doing that and you go around all the days of the week. But because 7 is a prime number, you can actually pick any step, and if you go Monday, Wednesday, Saturday, and you skip 2s, you'll actually complete all of the numbers as well. So we're getting closer. Let's try how this goes. I'm going to just say, rather than picking a random number, I'm going to add some kind of number like so. We're getting closer to what I would want. This is going to actually complete all of the dots, transitioning from one thing to another. But the problem is it doesn't really look very random. In fact, it looks very not random. Whether or not it's aesthetically pleasing, and I've used up my credit for pronouncing that word tonight, whether or not that's the case is up to your opinion, but it is going to complete all the dots in the required time. However, there is another piece of maths that we can use, which is that you can also find generators that work in multiplicative groups. And what we'd like to find is a generator for a multiplicative group that gives you this property of touching all of the different days of the week, if you like, but in our program here. And it turns out we can do that very simply if we list the, ooh, that's not going to work. If we list the program, I need to remember how to operate this thing. If we list the program, what we can do is simply change line 70 now to be that the new A is equal to the old A, oops, no backspace, the old A times 2, that's not going to work, times 2. It's actually surprisingly hard to type under this pressure. Now, behold, this function will touch all of these dots and it will produce exactly what I would have wanted in that primary school example eventually. It still takes a while because it's grinding through the maths, but we've found a generator that works to produce all of the different numbers that fit within the prime number set that covers the number of dots that we need to actually complete this square. So that's all well and good, and clearly I need to keep talking because otherwise you might not believe me that it's actually going to finish, but it should actually finish soon, except for the top left dot because multiplication by 0 is a different case, but I have enough typing ability here to be able to fix that one just by completing plot 0, 0. There we go. Done. Right. Now, thank you. What was the relevance of that, you might ask? I'm going to say there's 2 points of relevance. First of all, which numbers are generators of the multiplicative modular arithmetic group is actually hard to find, and it connects to cryptography. So you know how many generators there are because that's results that we have from Mathematics 4. Which ones are generators is not necessarily easy to find out. So I knew 2 because I tested it, and 2 is the first thing I tested, which happened to be a generator, so that was good. But this is crucial for cryptography, and that is crucial for cloud computing because cloud computing is always not where you are. Therefore, you need a link that goes over an untrusted connection between you and the cloud, and so all of the data needs to be encrypted. People don't remember this so much anymore because it's fairly easy to do encryption, but it is a fundamental building block. Less tenuously is the fact that I am showing you an Apple IIe operating on a MacBook Pro. So this is clearly not an Apple IIe. It's a lot lighter and smaller, has more colors on its display. The point is that we can take something that used to be a piece of hardware and turn it into a piece of software, and that's crucial. So let me take you on a journey through the lightning tour of computer security, and we'll also kind of bring up cloud computing as we go. 2001, this is the year we'll return to for a number of reasons. Embracing information technology there largely involved steadily filling machine rooms with computers. If you wanted to isolate 2 different database systems, the easiest way to do it was to have 2 physical servers. Air-gap security. So in other words, you have your database for your student records management system, your database for your finance system. They're on separate physical machines. So if you want to isolate more stuff, you just buy more hardware. This was a time when e-commerce was still a thing, as opposed to just being like commerce, which it is now. The problem is that the hardware is often highly underutilized. So those 2 separate physical machines are often going to be operating at, say, 10% of their maximum CPU use. This is a huge waste of resources because power-wise, computers typically work, switch them on and they start using an amount of energy. This is an amount of energy, by the way, that gesture. And if they get really busy, they use more energy. And then if they get less busy again, they go down to a sort of lower level of energy. The point is that you've got this base load and a variable load that have to add together in terms of what that computer is using with energy. Now, these numbers are basically wrong now, but they were right at some point in time. There's more types of resources that get wasted here with respect to this kind of duplication of hardware. You're wasting the energy to keep these computers on that aren't doing anything. You're wasting the equipment because you've got multiple computers when you shouldn't need that. You're even wasting the physical space. I mean, in general, it's just not a good way to work. Virtualization enables cloud computing. So the key point is that my Mac can pretend to be an Apple IIe. It does a pretty good job. So the hardware in the Apple IIe is being simulated by my Mac in software. So we take the physical computers and we make them virtual. This is the term virtualization, that process. So what cloud computing does for us is virtualization at massive scale. So that's how it gets these economies of scale and the efficiency gains. But what's also important is that it's not just enough to have virtualization work for the cloud. You also need security. What needs to happen is the cloud service providers need to insulate themselves from their clients, and that's because the clients need to be insulated from each other. So Xeno servers near Turing's rooms around 2001, that was the time that I was having the privilege of being able to take happy snaps like this picture of King's College over in Cambridge. I'd started my PhD, and at that time, the University of Cambridge Systems Research Group were working on a thing called Xeno servers. So they're proposing this system that can execute code supplied by an untrusted user, so there's a security angle, and they can charge this user for the resources consumed by the computations that they're using. So this is from a 1999 paper, but sometimes it takes a while to kind of build all the software stuff. So by 2001, they were starting to have real impact with this. And what ended up happening was they built a software system for supporting the virtualization at high efficiency. And this has got to be an academic talk, because I've got a happy snap of King's College, and then a happy snap of great research results from someone else's research papers in the middle here. But what you see in these bars is that the second bar from the black bar in each one of those groups is the performance of this so-called Xen hypervisor. And what you notice is it's very close to the black bar. The middle one is where it does worse. It's about 10% lower than the black bar. The other bars represent things like the leading commercial solution at the time. And so you can see, particularly from the database workload in the center, the Xen hypervisor is absolutely blasting away the competition in terms of how efficiently it works. And it happened to be this great combination of PhD research that came together to make this sort of perfect academic project that had real academic and industry impact. It kind of slightly passed me by, because I knew the people involved, but I was kind of looking at other things, although I did kind of get involved peripherally with what was happening with respect to Xen. What was interesting, though, is from the Xen system, it was noticed in terms of its impact by another player, namely this one. So it turns out that Amazon, when they started their cloud computing platform, actually used Cambridge's Xen hypervisor as the way of launching the cloud. So I really ended up being down the corridor from where the cloud actually started. Cloud virtualization is done by these things called hypervisors, and Xen is one which was developed by that Cambridge team. But virtualization is interesting because of the fact it supports security. So you can run this untrusted code inside a virtual machine, and you add this extra slice of software protection to make this work. So here we have two slightly dodgy looking clip art servers running at the bottom as the hardware on which we're running two operating systems, these separate physical machines, Linux and Windows, because virtualizing Mac OS is possible but weird because of licensing. And then you've got some applications that run over the top of that on server 1 and server 2. So what we do, this is just the case of a 2-to-1 kind of factor. We can transition to a world where we slide in the hypervisor between the hardware and the operating systems, and we can now contain in these gray regions these virtual machines. So the hypervisor Xen provided this layer of protection. But virtualization actually isn't a new thing. It's been in IBM mainframes since the 1960s. It's been around for a very long time. I often joke with students that one of the best ways of picking the next huge thing that's going to happen in computing is you look back 10 or 20 or 30 years, find something, give it a new name, and then bang, you've got the next big thing. But that is partly true, because there are things in cycles that change between decentralization and centralization that swing forwards and backwards with a slightly different context. But in this case, what was key was that the Xen system was very fast, was open source and free, and it put virtualization on commodity equipment. However, the cloud also has to track resource use. And this connects to sort of one of the other journeys that I've been able to go on, which has been really interesting and which has a lot of mileage left, which is tracking the provenance of data. So provenance describes the origin of data, and if you think about it in terms of art history, it describes where a piece of art's come from, whose hands it's passed through, that kind of information. Provenance can enrich data with context and semantics, and that's also true within computer science contexts as well. So two cases where you come across use of provenance in particular. One is reproducible computation. So if you've got a climate model that says everything is just fine, then you want to know how on earth it came up with that answer, because it's probably wrong. So how do you track that through? Provenance systems can kind of give you an idea of where the computation came from. Another example is explaining bugs in software. When something goes wrong, what happened? How do you figure out what that was wrong, and how do you fix it? This is important for security because bugs in software you often have a kind of security effect as well. So this is one of the crossovers there. There's an emerging area which I'm really keen to look at more, but which is only very early days, which is also looking at labeling data for our indigenous data sovereignty considerations. So that's going to be going forwards very interesting in terms of a national impact of where provenance research can go. So the research journey that I've had the privilege to share is in a topic called whole system provenance, where you basically get a computer system to explain everything that it's doing. And this was something where we got to make some sort of early results in this space. The challenge there is to avoid getting flooded with irrelevant noise, because computers do billions of things a second. So if you get a record of everything that's happening, you can easily flood yourself. And another admission I've got to make on this slide, I collect bugs, software bugs. So there's a couple of examples here of cases where I found bugs in software that you can use Provenance to track down, but I'll reveal the complete set for discussion. For example, here you have a password dialog box telling us that the password is too long after I've typed a single character into that box. It's also telling you that you've got a maximum of 16 characters, which is probably broken from a security perspective anyway. For those of us that have had the use of our old content management system for the website, then this is an example of where it was saying something was wrong, the following reasons, and a blank list. One of the ones that I enjoy is this one from Acrobat, where the software malfunctioned before it even got to the point of saying what the error was, and so you're just seeing internal programming code, and it's telling you, shh, bad news is coming. Okay. And the bottom examples here are where the major cloud providers have crashed and lost some of my data. So just to make sure that it's clear that the cloud isn't a perfect solution to this. So there's many challenges in terms of cloud computing. One aspect is that there are so many different stakeholders involved. And so I've looked at some of the cloud technology that's important, but there's a lot of human level complexity that's important as well. And this is an area where provenance is interesting because it allows a connection between the human and the technical. So I spend a lot of my time working with amazing researchers who are buried down in the depths of some operating system kernel. You can kind of look up the users that are far above you doing the application things. It's really important to make sure that these groups don't end up falling apart from each other. So provenance is where I'm looking to kind of join that gap together. So in terms of just the examples here, you see that you've got the cloud service providers, you've got the companies that use the cloud, you've got the end users that then use the software the cloud customers provide. And all of these sort of things to do with system administration and software developers, regulation, get more complicated in the cloud because everything is distributed across multiple different organizations. And then you've got law enforcement who want to know what's happening. You've got things happening across multiple jurisdictions. It all gets quite complicated quite quickly. So when it comes to that, what we want to have is cloud data processing be able to support this very dynamic, fast outsourcing of information processing, which happens, but we need to be able to do things like protect data, despite the fact it's traveling internationally around, and we also need to track how the data is changing hands. I often mention, in fact, even today's cloud lecture, when we started off the cloud paper today, talking about how the European Union has been a great benefit to us all, because Europe represents a big enough chunk of the technical population of use of software. It turns out that a lot of the things that the EU do actually benefit everyone. An example with respect to handling private data or personal data is the General Data Protection Regulation. That's been globally useful in terms of protecting us from some of the things that can go wrong with respect to sort of big commercial impacts. But there's many more things the EU has up its sleeve coming out with respect to the Digital Services Act, the Digital Markets Act, and the AI Act. I'm not talking much about AI tonight, but it's certainly another area where I've been able to join a journey in terms of looking at safety and security and trustworthiness with respect to that kind of technology. So I'm going to give you a very quick access control primer to describe where some other aspects of security fit and try to tie all of this together. Two main approaches that are applied for security: discretionary access control and mandatory access control. Discretionary access control is the typical type of thing you'll get when you're managing your own resources, files and folders on your own computer. You're the owner, you get to say who gets to do what with your data. Mandatory access control, on the other hand, is where you have something like intelligence services doing multi-level security. There you have these rules that are systematically applied to all the participants and all the data items, and you can express those rules and enforce them in a consistent way. So for example, you can't send top secret records to people that only have a secret label. Likewise, you cannot read top secret records if you yourself only have a secret label. These two types of access control appear to be something that, for example, Donald Trump has been confusing recently with respect to record management. But this is the problem that we have here is that mandatory access control is typically less convenient, which means we typically don't use it. However, it usually provides stronger guarantees, and it's one of the technologies that I'm definitely promoting. But in addition to that, and orthogonal to the access control, we also have this issue of fine-grained security. Now, what do I mean by that? Security designs implemented in software and hardware are often engineering focused. And what I mean by that is that the operating system design normally ends up influencing how all these concerns get written out in terms of what the operating system can enforce. So an operating system's job typically is to keep your applications, and here's two applications, left hand and right hand, that are kept separate from each other. Now let's consider one to be your email program and one to be a database of student records or something like that. You probably wouldn't do email on your database of student records. Anyway, let's go with that example for the sake of it. The operating system's job is to keep these two things isolated from each other. But the problem with that is that this database is handling sensitive information. And ideally, what you'd like is that the records inside this database are also protected from each other. But the operating system just sees it as an application. What we would like is the ability for the database to explain to the operating system how to help it do its own security, because then we abstract out the security management from the database software, and we can approach that with a consistent way from the operating system. That's what I mean by fine-grained security. Ideally, we move to a world where all data that the computer is handling in software has fine-grained security metadata. So we understand details about the meaning of that data and can thus understand how to delegate the enforcement to the operating system and make this kind of work effectively as a means of doing access control and security. So the final thing that needs to be kind of put into this mix is this notion of security capabilities. What are capabilities? Well, we know what capabilities are, but again, this is one of those things. What does it mean in a computer science sense? How has computer science taken this word and used it in some way? Capabilities in the computer science sense are a description of the embodiment of a permission to carry out some action. Now, I quite like this because it becomes a kind of unit of something that is kind of separate from other types of data. So you can see it's got this ability to have security metadata. You understand it's about something different from normal data. It's actually managing security. It allows you to factor out the security credentials as a different sort of data in your software, which improves the separation of concerns in terms of how you write your software. So a database writer can just write a database that does queries quickly. They don't have to worry about security because they're able to factor out the management of that security to something else. Now, my PhD thesis actually explored distributed capabilities, and I didn't really focus on that being the case, but this is the thread that's starting to run through what I've realized is this research journey. What I was looking at there was over the internet, over a network of systems, how could you do access control for decentralized electronic health records? So we implemented a way of representing policies for decision making in an access control engine, and that's all well and good. We explored whether or not the policies that we could represent were suitable for the types of health record management that were necessary. But one of the problems that I would love to fix, and hopefully we'll get the opportunity to fix, is that the enforcement of that security required the software to kind of interact with our access control engine. So we could answer questions about whether different users in a system should be allowed to do different things. But one of the big problems with software is that people often forget to check the access control rules. And so you leave off calling the access control engine, and that means that sometimes you're asking whether or not a particular security check occurs, and other times the software just left it out, which means you get security holes in your software. So what I would like would be to strengthen the way the enforcement can work, and that's where we'll try to join these bits together. This is largely bling graphics. You don't need to appreciate all the details here, but it's an example of another iteration of this journey down capability systems that's leading me to where I am today. And here, what I'm showing you is capabilities within what I've called a unique software engine. And by using the term unique, what I mean is it's really cool, but nobody uses it. But that's okay, because we didn't necessarily expect people were going to adopt this. One of the difficulties was we built this message passing infrastructure to allow this kind of really elegant handling of messages in a system that had security metadata associated with them. But the big problem is that you have to write all the software from scratch. And who wants to do that? There's a lot of software that already exists, and it's quite important to have a path from what's termed legacy software, meaning today's software, to use in new platforms that come out. So ideally, you find ways to wrap security around something that already exists. And in this particular example, what we were looking at was affecting what's called dark pool trading. And it's a bit surprising that this was happening literally pretty much in parallel with the global financial crisis. I don't think it had anything to do with us, but this is an example where we were looking at the labeling of data. If you're dealing with a stock exchange, and I'm going to go rapidly off my area of expertise pretty quickly here, but if you're dealing with a stock exchange, I understand that concept. You get buy and sell orders, I understand that as well. If you're a large merchant bank interacting with that stock exchange, you'll often get a large queue of buy and sell orders that you're going to try to get onto the exchange somehow. What we were interested in is showing that as an example where we could use this fancy security technology to allow us to do things like match buy and sell orders that were sitting within that organization before they got to the exchange without having to reveal who the buy and sell orders actually were for. So we could deal with these software components that had partial visibility of a particular message and could do intelligent and useful things without needing any more information than the limited focus of information they had in front of them. And this is a powerful model because it means you can make much more secure systems by putting these sort of boundaries around individual software components, knowing the overall design is going to cause the effect that you want in terms of the net outcome of this secure software. But like I said, the difficulty here was you had to write everything from scratch. So where are we now? We're moving now towards what I want to kind of conclude with as this promising trajectory leading forwards. Typical enforcement in the modern operating systems, again, work by this idea. You've got this all-powerful operating system kernel that's managing security on behalf of the whole operating system. But the problem is, operating system kernels are full of bugs, and we know that because we get software updates all the time. This is the type of thing that's getting fixed when people realize there are problems. Generally, there's a rule that you will have bugs in code for just a certain number of lines of code. There's a ratio that almost always holds true. And operating systems contain millions of lines of code, so they definitely still contain bugs, even when those bugs are being fixed. What we'd kind of like, though, is this ability, as I said, to get these user kind of processes like this database. They need to access privileges on a system. The security checks are often ad hoc. And this leads to this problem that you can get these flaws, as I mentioned, from the missing access control checks. And one analogy that only goes so far, but I'm going to run with it, is kind of like having a complicated road network. If you put kind of toll gates sprinkled through that road network, and we're talking about a really complicated road network, let's make it higher dimensional, so it's not even 2D. But you've got all these toll gates. You need to check whether or not there's reachability down all those different paths. What would be better for us is to have a stronger partitioning of traffic. So say road versus rail. Generally, trains don't get far on roads, and cars don't get that far on train tracks. That's an example of a kind of strong partitioning that we would like to have. Where could we seek to find that kind of strength of partitioning? Down in the CPU of these systems. So again, we come to something which is actually not a new idea. It was done in the 1970s, but it's happening again. This concept of memory capabilities. Memory capabilities are capabilities, that's security permission to do a thing, but they relate to access to data, the access to memory. So you're controlling access to the data that is in RAM, and they are controlled generally by the CPU. So this really means you can plant the security down low into the hardware of your system. And it means we can come towards a joining of the different components I'm talking about. Fine-grained, mandatory enforcement of the memory that is inside all of your programs, all the data there. This is absolutely ideal. Like I said, it's actually not a new idea. It was built in the Cambridge CAP computer, which became operational in 1976. Also, the Apple IIe came operational around that time, and so did I, in terms of things coming operational. And it turns out that the CAP computer, which nowadays doesn't do very much, I actually walked past that almost every day that I was doing my PhD work in the computer laboratory. And again, this might have been a bell ringing in the back of my mind saying capabilities, they're kind of important, they're actually your research theme, but I didn't really notice I was going to go and have a shower after riding my bike into the lab or whatever. The CAP computer is an example of a physical computer where every single item of the memory of that computer has additional security metadata included in the hardware. So every single data access has security checks applied. And for a security researcher, that sounds great. But it is generally the point, as I said, that we can move towards this fine-grained mandatory memory capabilities. But they're now coming back. New CPUs. Again, the University of Cambridge have been recently developing new CPU designs with security extensions. In particular, the project I'm referring to, which I'm certainly not directly involved with, but was, again, starting at the time that I was looking somewhere else in the computer laboratory, CHERRY, the Capability Hardware Enhanced Risk Instructions Design. And because computer science can never have enough of those abbreviations, that abbreviation contains an abbreviation, namely RISC. So I'll quickly go over what that is, although it's not particularly important. RISC is the Reduced Instruction Set Computer. So I just included that for completeness. Very broadly, RISC is why the new Apple chips run very quickly and at very low energy consumption compared to equivalent Intel chips. Intel has this legacy problem. They've chosen to support legacy technologies because that's a commercial decision for them, whereas Apple just chuck away any backwards compatibility every time they do something new, and they're really winning in this case because their new designs can really strongly embrace the RISC design. Anyway, that's just a way of making computers go fast. The cherry point is that you get the ability for your software to use CPU-enforced, fine-grained, mandatory memory security. Where this fits in terms of the cloud is that recently I've had the privilege of working with people at Imperial College London, and this is fairly recent work. This is only the last couple of years that this has sort of really started coming together. We've been rethinking virtualization for cloud computing. So we've come up with this way of using capabilities to create a virtual machine-like abstraction, but it's using memory capabilities to do the security isolation instead of the ways that virtual machines typically worked otherwise. And what this means is that we can get strong isolation of the different application components, which is what we want, but we're also getting to do it in a way that is safe and has very efficient sharing of data between these components. So this is really exciting, and hopefully I get to tell you more about that. But before I conclude on the research, I want to talk about another sense of having my head in the clouds. Oti Poti Dunedin, talking about settling here. And again, Giselle and I, when we first walked up Mount Cargill, we were about the same place, but we didn't even get to see the fact there was a microwave tower because the cloud was even thicker at that time. You could hear the wind whining through it, but we couldn't actually see it. So the setting in Dunedin, the community, the sunny people, and those of you who are here tonight, extremely pleased. Thank you for being here, and also the people who are online watching as well. It's been wonderful to settle in Dunedin. So the sunny people and the sometimes sunny weather. But the reality is that Dunedin's range of weather is just great anyway, because the weather is so contrasting and so constantly changing. But how many places would you have in an environment where you could go for a quick run at lunchtime and end up 600 meters above sea level, looking out over Dunedin? Or indeed, you can go home and end up above the clouds entirely. So you get your choice between above and below. And the rainbows, I guess, are just where the clouds sort of more around you in that sense. You get to, I mean, in my sense, this is a really something I very much enjoy about the natural environment, being able to be sort of out having a bit of a thinking break, being refreshed by the sleety hail and, ducking the odd flying tree branch. But for me, though, to continue actually seeing this wonderful environment, certainly recently, that's involved a fair bit of ophthalmology. And that's another aspect where I am very thankful for Dunedin. It's been another town in my sequence of towns that have excellent ophthalmologists to deal with which bits of the eyeball can be replaced or removed or stuck back on again and again and again, which has been the last kind of year. And again, I'm very well aware that this has fallen unduly in terms of inconvenience on Giselle and Robbie with respect to this. But the ophthalmologist, who I won't embarrass, but who was leading my care with respect to all of these different repairs, just represents so much of what I enjoy about Dunedin. He went way beyond the call of duty on multiple occasions, in ways I won't tell you the details about, but was still really touching in terms of just what was just assumed to be what he would do to support patients and the recovery that I've been able to enjoy. Although, of course, I'd also say that because I'm in for iDoc again come November, because we're going to try to fix the right one. Anyway, we'll see how that goes. So Dunedin has given me a vast number of opportunities for running around like crazy, which I very much enjoy, both physically and mentally. So the University of Otago, we've heard about the teaching, the research, and the service, and I very much appreciate introductions there. The scales of collaboration, local within the department, national and international, and in terms of life in general, between family and friends and colleagues. But the question you might ask, at least I hope you would be, what if you plotted where I was if I only got halfway to the next thing I'm trying to get to in terms of this particular triangle of sets of threes of things? Well, it turns out I can kind of answer your question because I've got something handy here already. If we were going to look at this particular program, I'll show you that now we're changing to high resolution graphics, which is comparatively higher, but not particularly high. We're picking a color, we're kind of putting in some coordinates here. Line 30, we're going to choose which of the particular things, the different endpoints I'm running towards in this triangle, and then we make a couple of decisions. Basically, we say Tx and Ty are the target X and target Y that I want to move to. 70 and 80, those lines move me halfway towards any of those particular targets, and we plot a point. What do we get? Well, you get some dots. That's the problem with these machines, is they're so slow that the actual picture may not emerge quite as quickly as you might like. But I can cheat, because of course it's not a real Apple IIe, so I can just fast forward you to a state that I saved earlier. It's still going, but here we go. It's a skip forwards a little bit in terms of time. And an interesting property of these machines is they're largely deterministic, because I don't even have a clock. They don't even know what the time of day is. So I can teleport them forwards and backwards in virtual machines without it being a problem. Anyway, this represents a fractal triangle in a kind of slightly ugly detail. So I've got one here that's a little bit more kind of vectorized. The point here, though, is that while I'm extremely well aware of my kind of finite time and the ability to run between all the different interactions I've had, well, it kind of feels like the richness is the infinite circumference that still can fit within that finite area. And again, how could one find a geekier way of saying thanks to all of you than that? But I'm not done. I've got a bit more thanking. Key formative experiences. Again, thank you to my parents. It's great to have you both here. The academic steering or nudging that was necessary at various times. My sister and her family in Sydney. And again, all of the friends and family worldwide. Giselle and I have lived in Australia and the UK and New Zealand. And we've had countless fantastic opportunities to engage with wonderful people all around the world. And these people had really lasting and very positive effects, of course, on all of my experiences. Then there's also, more local to home as well, our caffeine-fueled CST room. Not necessarily everyone's completely caffeine-fueled, but certainly I am. And so again, I'm very thankful to all the interactions I've got to have in the department, because this has sort of really been formative for where I've been able to go. So thank you again, but I'm still not done. In terms of the last phase, or the most recent phase of thanks that I would give, my world was certainly turned upside down by this guy. And of course, this is a sort of privacy-preserving photo, because it's kind of like, that's a baby, which is true. But nonetheless, this was a complete revolution in terms of my life. And I was thinking there that, actually, when talking about this and the thanks that I have for Giselle and Robbie, that there was a slight possibility that I might even get kind of emotional. I don't normally lecture about, my family. So I thought that it might be about now that it could be a time to kind of consider a very useful reflection of the essence of my communication style that was provided to me at one time by my PhD supervisor in Cambridge. And so as a consequence of that, I will allow the next slide to simply, this is my second last slide, to stay on screen for long enough. This is another case where I have kind of applied a kind of privacy preserving technique. You can see that Giselle and Robbie have legs, and that's about as much detail as you'll pick out from this imagery. There's also the point down the bottom, which you can read and possibly use as a talking point when we move to refreshments later on. But to conclude on the research front, I would like to say that as this day ends, and we look forward to the days that come in future, cloud computing is going to have an ever-increasing impact. There's a ton of different security and data provenance tracking challenges that we still have. But what's been really great is to see that actually, I think these building blocks, speaking as an engineer, are starting to fit together to show that there is real promise in this idea of taking fine-grained mandatory security and actually being able to apply it in really practical contexts for cloud computing. So I'm hoping that that continues, particularly supported by this idea of the CPU memory capabilities that I feel are going to be able to transform cloud security. So on that note, what I can say one thing for sure is that I very much hope this is to be continued. Thanks, Steve.
Tēnā koe, Professor Barker, tēnā koe, Professor Blakey, tēnā koe, Professor Ayers. Tēnā koutou, and welcome to all of the friends and family gathered here today to help celebrate Dave's tremendous achievement on attaining the lofty ranks of professorship. For those of you who don't know me, I'm Stephen Mills. I'm currently Head of Department of Computer Science, but as we've heard, I may soon have the distinction of being the shortest-lived Head of Department in the history, a record that can never be taken from me. It's been, and I also took up the role at the start of the year, and so this is my inaugural professorial lecture closing, and it's the only one I'll have a chance to do, at least within the department. And it's a great pleasure for me personally that it's Dave. I've had the great privilege of working with Dave in teaching, in research, in service, and all of my interactions with him have been tremendous. And it is so great to see all of his hard work being rewarded with this promotion. I was thinking about things I could say about Dave. I'm going to say some nice things. I'm going to say something, people always say nice things at the moment, so I'll start with something else, which is about imposter syndrome. So imposter syndrome is the feeling you get that you've just faked it to be here, and it's something a lot of academics have. The negative thing I'll say about Dave is he triggers my imposter syndrome.
Apologies.
There are different types of computer scientists. Some of us like what you can do with computers. Some of us like computers. Dave likes both, and he's very good at both. I just like what we can do with computers, so whenever he starts talking about how they actually work, I think, they're going to catch me soon. I was also thinking, there's a lot of words I could use to describe Dave, but one that occurred to me when I was sitting there that hadn't really occurred to me before is brave. I think Dave is a very brave man because he has two characteristics, which I think you saw. One is the ability to attract technical glitches and bugs. There are things that happen to Dave that don't happen to other people that reflect the deep inner workings of computers. The other one is his desire to put live demos into all of his talks. And this makes him a truly brave man. I've also had the privilege of teaching with Dave on a number of courses, and I'm always reassured when Dave's there because I know I don't have to worry about any of the technical stuff. He'll just sort that out. Even if it involves some very lengthy, what he refers to as yak shaving scripts in order to automate various university systems so he doesn't have to click on anything. Dave will quite happily spend a week automating a 10-minute task. But as you've seen, Dave's communication is excellent. There are a number of different feelings you have after an academic gives a talk. The most common one is confused and frustrated. More positive ones that you can feel are, that person's really bright, or I feel really smart because I understood what was going on. And Dave has an uncanny knack of doing both of those last two at the same time. And this is also something I've seen in his lectures to undergraduates, his ability to explain complex things in quite a lot of detail, but in a way that's accessible and understandable and lets people take away their understanding of that is truly tremendous. In terms of research, I've had the honour to work with Dave on a number of research projects. I've admired his commitment to the projects and also his ability to really get to the heart of what the research questions are. And this insight into what's really going on and what the key things to explore are, I think is what's led Dave on his path, which he feels it's meandering, but I think it's always heading towards the right things. So there's a few other jobs I have to do before we finish up, and I've been warned not to take too long. Dave managed to finish with 12 seconds on the clock, which is tremendous. So my next duty is to present Dave with a token of our appreciation for all of his work and a reminder, and I'm reliably told to be down there, of this day and your promotion. So this is for you. Congratulations again.
Thank you very much. Thank you.
I'd like to thank you all for coming out and supporting Dave tonight, and also thank all the people who are watching online or on recording. I know that Dave has got connections around the world, and people are thinking of him who can't be here today. And so thank you to all of you for coming along. And thanks to Dave once again for his IPL, which has been truly enlightening. And my final formal duty of the evening is to invite you all to join us back at the Staff Club for drinks and refreshments to join Dave in again celebrating his well-deserved promotion. Kia ora.